Good afternoon, dear students of Standard 11. How are you? Hope you all are fine by the grace of Almighty Allah. Today, I am here to explain some topics from your chapter 1 of physics second paper, that is thermodynamics. And today I will explain work done in different thermodynamic processes. Dear students, we have already well known about different thermodynamic processes, and you know there are three thermodynamic processes. One is isobaric process, isoporic process, isothermal process, and adiabatic process. So today I will explain about the work done in those thermodynamic processes. So at first, work done in isobaric process. You know from the name isobaric, iso means same and bar means pressure. So isobaric means same pressure. So look here, A to B, the pressure remains constant. That's why it is expressed by using a straight line. But look here, the volume is not constant. Rather, volume is changing from VA to VB. That means here initial volume is VA and final volume is VB. So in order to change the volume, there must be there must have done work, and that work can be calculated by calculating the area from this graph. That means this area which is below the line AB. Okay, so by calculating the area below the line AB, we can calculate the amount of work done. So work done in isobaric process is what? Del W equal to P del V. That means, look here, area means length into breadth. So here length is what? Length is expressed by this pressure and breadth by the change of volume. So here pressure remains constant, that is P, and del V, that is change of volume, that means VB minus VA equal to del V. So the product of pressure and the change of volume is the work done in isobaric process. And you have seen in isobaric process there is no change of volume. That means in isobaric process volume is constant but pressure is changing. So in isobaric process, as the volume is constant, there is no work done. That means if in MCQ type of question, if this question comes, what is the work done in isobaric process, it will just put the value of 0, because in isobaric process there is no change of volume. That's why work done equal to 0. And in isobaric process, work done equal to P del V. Let us calculate the work done in isothermal process. Look, here by using this graph, I am making it clear about isothermal process. Isothermal process is that process where temperature remains constant. You know about isothermal process, and you have also well known about it that isothermal process follows Boyle's law. That means PV equal to constant. So look here, pressure versus volume graph is shown here. So look here, pressure from this graph you can understand pressure is inversely proportional to the volume. That means if pressure is increased, then volume will be decreased, and if pressure is decreased, then volume will be increased. That's why pressure and volume are inversely proportional to each other. And here this is the isothermal curve. So in order to calculate the work done from this graph, we have to calculate the area that is below this curve line, PQ. Okay, that means A, B, C, D. This area we have to calculate to find out the work done in isothermal process. But before explaining it, I will tell you one thing. In isobaric process, you have seen at that time also we have calculated the amount of work done by using the graph, but that time the area was a rectangular area. Okay, and it was very easy to calculate the area of rectangular area because it is only length into breadth, but here the area lies below this curved line, and it is very difficult to calculate it by the general formula of length into breadth. Rather, we have to calculate this area by using integration method. So look here, work done in isothermal process. The isotherm PQ for the process is shown in the figure. The net work done to expand the gas from a volume V1 to V2. In the graph I have written Vi and Vf. That is also true. That means initial volume is Vi and final volume is Vf. You can also take V1 and final volume as V2. No problem will be there. So the net work done to expand the gas from volume V1 to V2 will be work done equal to area ABCD. Thus, area occupied below the curve in between AB and CD is gives the required value of work done. So let us look how can we calculate the work done. So analytically, we can be calculated by integrating dW between the limits V1 to V2. Look here, dW, that means the amount of work is done when the volume changes from V1 to V2. So we have to integrate dW in the limit of V1 to V2. So W equal to integration of 0 to W, dW equal to integration of V1 to V2 PdV. You know dW equal to PdV. So we put the value of dW here, PdV, and the volume change. The lower limit of the volume is V1 and upper limit of the volume is V2. For a perfect gas, V equal to RT. That is, that you know from Boyle's law, that Boyle's law always follows. Isothermal process always follows Boyle's law. That means it follows PV equal to constant. So we can write PV equal to RT. From here, we can write P equal to RT by V. Now, we will substitute this value in the equation, above equation. Then we will get W equal to integration of V1 to V2 RT by V dV. Dear students, here R is molar gas constant and T, this temperature, you know, in isothermal process temperature remains constant. So these two terms are constant. So we can take it outside of integration. So as temperature is constant during isothermal expansion and R is a gas constant, so we can write W equal to RT integration of V1 to V2 dV by V. R equal to RT log E base V or ln V. Lower limit is V1 and upper limit is V2. Dear students, integration of 1 by x dx equal to ln x. This is the formula, and that formula we are using here. Okay, that means integration of 1 by V dV equal to ln V. Okay, so we can write W equal to RT into ln V2 minus ln V1. Look here, in case of V, we can put the value of upper limit and lower limit. So it becomes ln V2 minus ln V1. And it can be written as also RT ln V2 by V1 in this way. So this is the work done in isothermal process, where work done equal to RT ln V2 by V1. For N mole, we can write W equal to nRT ln V2 by V1. And you have to memorize this formula. Now I will show you how to calculate the work done in adiabatic process. Look, this graph shows adiabatic process and adiabatic expansion. You know, adiabatic expansion also. Here we are also getting one curved line. This adiabatic curve, but this curve is little bit sharper than that of the isothermal curve. And why it is sharper? I have also explained that in the previous content. So look here. Here we are seeing this as the adiabatic curve, and adiabatic process is different than that of the isothermal process. You know it, isn't it? This case is different from the case of isothermal change in two respects. That is, number one, the container is made up an insulating material, and number two, the curve is much sharper. The adiabatic curve PQ for the process is shown in the figure. The net work done to expand the gas from the volume V1 to V2 will be the area, W equal to area ABCD, which lies below the curve line PQ. Okay, that means the area occupied between AB and CD represents the work done in adiabatic process. Now, mathematically I will show you how to calculate this work done. Analytically, net work W can be calculated by integrating dW between the limits V1 and V2. So, W equal to integration of 0 to W dW, integration of V1 to V2 PdV, equation 1. You know, for adiabatic change, it also follows Boyle's law, but in a different way. In this case, PV equal to constant will not be applied. Here, PV to the power gamma equal to constant will be applied. So, you can write PV to the power gamma equal to constant. Suppose that constant is K. So, PV to the power gamma equal to K. So, from here we can write P equal to K by V to the power gamma. And we will put the value of P in the above equation number 1. So, equation 1 gives W equal to integration of V1 to V2 K by V to the power gamma dV. K into integration of V1 to V2. So, 1 by V to the power gamma can be written as V to the power minus gamma dV. So, here we will use one formula, that is another formula of integration. Look, integration of x to the power n dx equal to x to the power n plus 1 divided by n plus 1. That means you will add 1 with the power and divide with the same thing the numerator. So, x to the power n plus 1 divided by n plus 1. Suppose here integration of x cube dx, then what will happen? It will be x to the power 4 by 4. That means x to the power 3 plus 1 divided by 3 plus 1. So, it will be x to the power 4 by 4. So, in this way, we can integrate in a function. That means integration of x to the power n equal to x to the power n plus 1 divided by n plus 1. So, we will use this formula for calculating this here. So, W equal to K is constant. We have taken it outside. So, V to the power minus gamma, it can be written as V to the power minus gamma plus 1. But minus gamma plus 1 can be written as 1 minus gamma, isn't it? So, we can write V to the power 1 minus gamma divided by minus gamma plus 1. That means 1 minus gamma. Lower limit V1 and upper limit V2. So, it becomes K by 1 minus gamma into V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. Here we put the value of limit. So, here, you know, for adiabatic process, PV to the power gamma equal to constant. So, we can write P1 V1 to the power gamma equal to P2 V2 to the power gamma equal to constant K. But from the previous slide, we get W equal to K by 1 minus gamma into V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma. So, we can multiply this K with the term inside the bracket. So, at that time it will be 1 by 1 minus gamma into K V2 to the power 1 minus gamma minus K V1 to the power 1 minus gamma. Okay, we can write that but I skip here that line. So W equal to 1 by 1 minus gamma. We have multiplied K inside, and in place of K, if we multiply K with the both term, then in place of K we can write P2 here V2, so we can write this one P2 V2 to the power gamma, and here V1, so we can write P1 V1 to the power gamma. So look here, P2 V2 to the power gamma into V2 to the power 1 minus gamma minus P1 V1 to the power gamma V1 to the power 1 minus gamma. So that look here, P2 V2 to the power gamma, and V2 to the power 1 minus gamma can be written as V2 to the power 1 into V2 to the power minus gamma, isn't it? It can be written. Similarly, minus P1 V1 to the power gamma into V1 to the power 1 and V1 to the power minus gamma. So look here, V2 to the power gamma and V2 to the power minus gamma can be cancel out each other, isn't it? Similarly here also, V1 to the power gamma and V1 to the power minus gamma, they can cancel each other. So what will remain? W equal to 1 by 1 minus gamma into P2 V2 minus P1 V1. Equation 2. If T1 and T2 are the initial and final temperature of the gas, you know in adiabatic process, temperature doesn't remain constant, but in isothermal process you have seen that temperature remains constant. So here, if the initial temperature is T1 and then final temperature will be T2. So we can write P1 V1 equal to nR T1 and P2 V2 equal to nR T2. We can write because PV equal to nRT, that is ideal gas equation, you know it. So now we can put the value of P1 V1 and P2 V2 in the above equation, equation number 2. So it becomes W equal to, and if I put here nRT2 and nRT1, so N and R, these are constant, so we can take it outside because R is molar gas constant and N is the number of mole, so we can take it. So it will be nR by 1 minus gamma into T2 minus T1, and that is the formula for calculating work done in adiabatic process. So we got the 3 formulas, that is in isobaric process the work done W equal to P del V, and in isoporic process the work done will be 0. In isothermal process work done will be nRT ln V2 by V1, and in adiabatic process W equal to nR by 1 minus gamma into T2 minus T1. So these formulas are very much important for your mathematical problem, and using this formula creative questions can come in the exam. So dear students, I want to request to you, you must practice this derivation by writing in your copy step by step, and then I know you will feel it, you will understand it very well, and you will love it. And you must try some mathematical problem related to these formulas from your book, that is which book you follow, that means the book written by Dr. Shajan Tapur or Amir Hussain, any one of the book you can practice. And I will also declare about the date of the test. I will also take a test on these topics, and I will give that notice in the messenger test. So dear students, I want to finish my lecture today. There is a nice moral for you. Success is not the key to happiness. Happiness is the key to success. If you love what you are doing, you will be successful. Goodbye everybody.